Okay, good morning to you all. And today we are going to discuss another new topic. This topic is named as Design of Cryogenic Systems, Cryostats, and Transfer Lines. Okay, so this is a topic which we are going to discuss today. Okay, what is the plan of this presentation is like this. First of all, we will introduce the basic concept of a cryogenic system. Now, the cryogenic system, as you are aware, it can be a storage device or it can be an experimental cryostat where you would perform low temperature experiments. Then we would like to discuss about what are the design aspects of this cryogenic system. So particularly, you should choose the right materials which are compatible for cryogenic temperatures. And you should see what will be the strength at cryogenic temperatures for these materials. What is the effect of thermal contraction? Then the wall thicknesses of if you are having a storage vessel or a cryostat, the wall thicknesses of the vessel should be designed by certain standard formulas which are based on ASME Section 8 pressure codes, and also the fabrication procedures or techniques which one will be using for these systems. Now we will move on to the typical cryogenic systems. Basic cryogenic system can be storage device, first of all. It can be a glass device or a metal device. So we'll discuss the design of such systems. Then we'll come to the experimental cryostats. Again, they can be made out of glass and metal. There are other type of cryostats. For example, continuous flow type cryostats are there. Okay, and one more thing is people these days use cryocoolers. As you know, cryocoolers or cryorefrigerators essentially replace your cryogenic fluids. In place of cryogenic fluids, you use cryocoolers because they are able to produce a certain amount of cooling power at the zone where it is required. So it requires a housing, and that should be certainly a vacuum jacket as well as radiation shields. So these things will be discussed next. Finally, there are many special cryogenic systems. For example, maybe the Large Hadron Collider or ITER, etc. So this also will need to be discussed. Then to transfer cryogenic fluids, you require cryogenic transfer lines. The transfer lines can be rigid, it can be flexible transfer lines, it can be made of different materials, particularly if you are looking for flexible transfer lines. The transfer lines can be made out of stainless steel bellows. Now you can have a simple transfer line without any insulation, because if you are looking for a short transfer, you can use a simple transfer line, nothing but a pipe, and you do the pressurization and the liquid comes to the other side. Then you can think of just vacuum insulated transfer line, then multi-layer insulated transfer lines, etc. can be there. Okay, we are not still discussed about thermal insulation, but we will discuss thermal insulation probably as a next topic. So what about the spaces between the lines, between the pipes, and then the joint? Suppose I want to make two transfer lines, and they have to be joined. So what sort of adaptation is required? These things will be discussed. Lastly, we need to also have suitable walls, which will either open or close so that cryogenic fluid can be made available or it can be shut off. Okay, so what are the designs of cryogenic walls? Then lastly, in the cryogenic system, you always require to take care of safeties. Okay, so you need to talk about the safeties of cryogenic fluids. Okay, these things have to be done. Okay, so we will conclude the lecture at the end of this. Okay, Let us start with the concept of cryogenic system. A cryogenic system can be defined as a space where the cryogenic conditions exist. Say, for example, a storage container of a cryogenic fluid is a cryogenic system. Similarly, an experimental cryostat, again for achieving cryogenic conditions, is a cryogenic system. As we have seen, for example, in our earlier lecture, the glass Dewar, as demonstrated by Sir James Dewar, is a cryogenic system. And you can see in the figure, adjoining figure that is here, a glass Dewar is being demonstrated by Sir James Dewar. Okay. Okay. If I would like to have a, let's say, a cryogenic system, then what is the way in which I can achieve it? So you require certain criteria for the cryogenic system, and they are the following. One is the cryogenic system should have the material compatibility for the cryogenic conditions. That means you can use only suitable materials which can be adapted for low temperatures. Second, it should have adequate strength for performing the cryogenic related task, or maybe, for example, the dimensions, etc. For example, 100-liter Dewar, so the volume of it should be 100 liters, things like that. So it should have the adequate strength to carry out these cryogenic related works. Then we require to reduce the heat transfer by the different modes into such system, because otherwise you will have to consume large quantity of cryogenic fluids. And also the safety aspects of this are very important to be taken care of. Okay. Now let's go one by one. We'll start with the design aspects. First, let us talk about the various things that are involved here. One is the material compatibility at cryogenic temperatures, which means that the material has to be ductile and non-brittle. Okay, so it should be compatible for low temperature work. Okay, you cannot use a material which becomes a ductile, which becomes a brittle material. Okay, sorry. Okay. Now, the main aspects to be considered are, for example, the strength and the ductility, thermal properties, and also the contraction, thermal contraction, and also it should be able to withstand the operating pressures that are designed for it, right? So these are something very important which to be taken care of. Okay. Now, what about the heat transfer? The heat transfer has to be minimal, okay, and the design should make sure that the heat transfer by all the different modes, such as conduction, convection, radiation, should be considerably reduced. And also, you must evolve an easy fabrication method for making this entire system, cryogenic system, right? So, and then you should work out the procedure step by step, which you will use in fabricating that system. Let's come to strength and ductility. Most materials improve in their strength at cryogenic temperatures. For example, ductile material should be used and should not be brittle. Okay, it should not undergo a ductile to brittle transition. Such materials have to be used for making a cryogenic container or cryogenic cryostat. Say, metals with FCC structure, face-centered cubic structure, copper nickel alloys, it's called cupronickel, aluminum and its alloys, austenitic stainless steels, normally these steels will have nickel greater than 7%. They are ductile down to very low temperatures. So they are quite suitable for example, for making cryostats or cryogenic systems. So metals such as iron, carbon steels, low alloy steels, molybdenum, niobium, they have body-centered cubic structure, or they call it as BCC structure. They become brittle at low temperatures, and hence they are not suitable for low temperature applications. Okay, but there are conditions. For example, you may have to use niobium, etc. under certain conditions. But anyway, those things have to be done with a lot of care, right? Plastics and polyesters, they normally become brittle at low temperatures. But PTFE or polyfluorotetraethylene, this is an exception. It remains ductile and deforms down to 4 Kelvin. So it is quite suitable. Now let's come to thermal properties. Now the thermal properties of the material what you are choosing should normally depends on the end application and also ease of fabrication. What do you mean by thermal properties? For example, a material, the thermal property can be, for example, it can be the thermal conductivity can be very high, or specific heat can be very high. Okay, or in some cases it can be very low. Okay, so for example, if I have to make the neck tube for a storage container, it should allow only minimal heat transfer. It should have a low thermal conductivity and low specific heat. So you can use, for example, glass or FRP, thin wall stainless steel tube or bellow, so that there is a long heat transfer path should be made available for minimal heat transfer. If I want to make a heat exchanger, this requires again materials like copper, aluminum, silver, etc., which will allow high heat transfer. They have high thermal conductivity and high specific heats. So they are required for such purposes. Suppose I want to make a heater. Now the heater should have almost constant resistance over the entire temperature range. So material which is suitable for this purpose is, for example, manganese, Kanthal, nichrome, etc. If I have to make a regenerator, the regenerator should be porous to allow the gas flow and also should have the maximum specific heat. Okay. Now, let us start with the storage containers. What should be the shape of a storage container? The storage container shape should be such that it has the maximum volume for a given surface area. So ideal shape will be, for example, spherical. Say, for example, you see in the photograph, a spherical container, a small size spherical container. But when you increase the size of the container, it may not be always possible to make spherical vessels. So what people do is they use cylindrical containers with the dish joints. For example, you see a cylindrical container with the dish joints both at the top as well as at the bottom. For example, this is a liquid nitrogen stainless steel liquid nitrogen tank. Again, this is having a cylindrical, it's a vertical type container. So it has cylindrical dish joints at the top and similarly cylindrical dish joints at the bottom. When you come to experimental cryostats, it depends on the user. So entirely it will be based on the user requirements, and therefore, for example, it can be just a cylinder with the top and bottom flat completely. Okay. Now let's address the thermal contraction. Thermal contraction happens in all materials, but when you combine different materials, thermal contraction should be such that the material which goes innermost should have lower thermal contraction compared to the material which is on the upper side. For example, here we see a joint of stainless steel with the copper and then brass. Copper has a larger thermal contraction compared to copper has a larger thermal contraction compared to stainless steel, and brass has a larger thermal contraction compared to copper. Therefore, if we arrange in this order such that the brass has a largest diameter, then followed by copper, and then followed by stainless steel, then as this particular joint is cooled, then the thermal contraction happens, but the joint becomes more strong. Okay, it will not give way. So care has to be exercised in the design of such type of joints, looking into the thermal contraction data. Okay, many times you may have to do repeated cooling and heating so that it has to be made sure that it doesn't cause any leakage. This is what is called thermal cycling. Normally, you also have other arrangements. For example, here there is a design given for stainless steel flange connection using a brass bolt with a stainless steel washer. Or, for example, you may need to have the feed-throughs connections with epoxies, and which is the right way, which is the wrong way, etc., are shown in this photograph, in this picture. The thermal conductivity data is normally provided in the form of an integral value. That is, for example, the change in thermal conductivity, change in the thermal contraction data per unit length over a temperature range is given. Okay, and it is always noticed. For example, I will just show the table. So, in other words, DL by L is what is DL is given for different temperature ranges, complete ranges, starting from not just the value of alpha, but it is nothing but integral T1 to Tt alpha dt. Alpha is your thermal contraction coefficient or thermal expansion coefficient. And if you integrate it, you get the overall thermal contraction over a temperature range, right? So now we can see the data which is given in the next page. Okay, cumulative thermal contraction or expansion per unit length for different materials are given in this table. So you see, for example, the temperature starting with 0 Kelvin to 300 Kelvin, and you have the values are given in units of 1 into 10 to the power minus 5. And the materials chosen here are stainless steel, brass, copper, aluminum, nylon, and Teflon. The last two materials are non-metals. Obviously, what you find is at around 300 K, the thermal contraction values for nylon and Teflon are fairly large. So, okay, whereas in the case of stainless steel, it's only 0.3%. Okay, and so you can see this, the values are 10 to the power 5, so it's about 304, 397. Copper is some value which I am not able to see here in the table. But anyway, Teflon is around 1600. Okay, you can see. So that means the non-metals shrink much more compared to metals, right? Okay, this has to be taken care, particularly when you have long lengths of the sizes of the geometrical shapes of your system, may be particularly applicable for transfer lines. Now, I am going to discuss to you about a typical cryogenic vessel. Okay, how does it look like? Okay. Now, you see on your picture in the screen, a typical cryogenic vessel. First of all, there are two vessels. There is an inner vessel and there is an outer vessel. So, this is an inner vessel and then there is an outer vessel. What about the in-between space? It is filled with a particular insulation. It can be a powder insulation or it can be super insulation or whatever may be the insulation, it will be filled in between. Okay. The wall thickness of these vessels, first of all, ought to be determined by ASME, okay, American Society of Mechanical Engineers, okay, boiler and pressure vessel code, section 8. I think this is in 1983. Maybe there are better versions available now. And this is unfired pressure vessels. You can also choose British Standard Institution standards. So it is 1,500 or 1,515. Now, what you do is you design the vessels for both bursting and buckling loads. Now, please understand, the bursting of the vessel happens when the internal pressure is very high. Okay, so the vessel bursts. The buckling happens, for example, when the vessel is actually evacuated and the outside is having the high pressure. So the vessel buckles. Okay, that's what happens. Okay. All the design formulas are given in the cryogenic system books, in the mini cryogenic system books, and also particularly the book by Randall F. Barron. And that book is also named as Cryogenic System. It's a second edition, Oxford Press, New York, 1985. Okay. Now, let us look at the drawing once again. It contains a set of pipes. okay, which is, for example, which is a diffuser. So it is connected to the vent line. And if you want to pressurize the cryogenic tank, you can also use that same thing. Okay, the cryogenic liquid is in there. So there is a manway, access manway you can see here, and there are pipelines which is used for filling and emptying. Okay, that pipelines are available. And you can see here stiffening rings and main support rings are all there, both for the inner vessel and outer vessel. These are required so that the wall thickness of the main shell is as low as possible, so that the vessel need not be designed to very high wall thickness. So the weight, self weight will be very high. To reduce that, in place of that, one uses stiffening ring and main support rings. Okay. Now there are support structures are available or there from the outer vessel to the inner vessel. Now the structure, what is not shown here is the bottom support. The outer vessel has to be supported on maybe a trolley or a set of wheels, so that the vessel can be moved from one location to another, right? So that is not shown in this picture. Okay. Now, other than that, what is not shown here also is, for example, the evacuation port on the outer vessel. Okay, the interspace has to be fully evacuated. So that evacuation port is not shown. So that is added on. And additionally, for example, one also has to have safeties. Appropriate safeties have to be provided. So for example, the inner vessel will be connected to an inner vessel, and its contents will be connected to a safety, so that if you are not using the cryogenic fluids, by external heat, it will continuously warm up. So once the pressure exceeds a certain value, then the vapors of nitrogen will go through that, right? So this is the way it is done. Okay. Well, these are more or less the typical of a cryogenic tank. Okay. Now let's move on. Now, as I mentioned, you require to use ASME Section 8 unfired pressure vessel codes for the design of the cryogenic vessels. For example, if I have to design inner vessel, then the wall thickness, there is a certain formula. This formula you will find also in Barron book. Okay, I have in fact taken from the Barron book only. It is, for example, what is the wall thickness of the inner vessel? Okay, what sort of sheet I have to take for proceeding with this one. Now, T is equal to product of P into DII divided by 2 times SAEW minus 1.2P bracket closed. Now, in this, T is the minimum thickness of the inner vessel. P is the design pressure. Okay. And DII is the inner diameter of the inner vessel. And SA is the allowable stress for the material of the inner vessel. And EW is the weld efficiency. So you use this formula, okay, and using this, we'll be able to calculate what should be the thickness for the vessel what you are designing. Now, as you see in the previous diagram, the vessel what is shown here is actually a cylindrical vessel with the disjoints on either side, right? So therefore, for this, you have hemispherical disjoints. Now, this hemispherical disjoint wall thickness also has to be calculated, and it is done using this following formula. THI is equal to, because the hemispherical inner diameter, so this is equal to, the wall thickness should be equal to THI is equal to P into DII K divided by in brackets 2 SAEW minus 0.2 times P. Okay, here THI is the minimum diameter of the hemispherical end. The factor K is given by K is equal to 1/6 of 2 plus D major plus D major plus D minimum D minor whole square, and the bracket is again closed. These are the major and minor diameter of the elliptical ends. That means the dish is chosen, the dish ends are chosen as part of an elliptical structure. And the elliptical structure will have the major and minor diameter, and that numbers are introduced in this factor K. Right. Okay, how do we design the outer vessel? Just excuse me for a minute. I'm sorry for the delay. I need to use my collar. Okay, the outer vessel has to be designed based on the buckling or collapsing pressure. The outer vessel will be mostly at ambient temperature and outside will have atmospheric pressure. So what you will be doing is you will try to evacuate the interspace between the outer shell and the inner vessel. So the interspace is going to be evacuated. Now the critical pressure as far as the ASME standards are concerned is 4 times PA, where PA represents the atmospheric pressure. So why do we choose this? A factor of safety of 4 that is selected in this case. Now again, for calculating the wall thickness, you require to know whether it's a long cylinder or a short cylinder. Now, a long cylinder is defined as one for which the length to diameter ratio meets the following condition. H divided by DOO is much greater than 1.14 into 1 minus mu square whole to the power 1/4 into D0 by T0 to the power half. Okay. The parameters are like this. H represents the height of the cylinder. DOO represents the diameter, outside diameter of the outer shell. And the T0 represents the minimum thickness of the outer shell. And mu represents the Poisson's ratio of the shell material. Okay, so if you plug in all the numbers, all these numbers into the above equation, so you can calculate this H by DOO, and that will tell you. So if this value is greater than the RHS value, then long cylinder, it becomes a long cylinder. If it is not, then it is called a short cylinder, right? Now, if it is a short cylinder, now we can, sorry, before we proceed, the outer vessel has to be designed, as I mentioned, in terms of the collapsing pressure for a very long cylinder. And this formula is given by PC is equal to 2E T0 by D0 to the cube divided by 1 minus mu square. Here again, E is the Young's modulus of the material. T0 is the minimum thickness of the shell. D0 is the outer shell diameter. And mu is the Poisson's ratio. Okay, so you again introduce all these numbers so that you can calculate the critical pressure. Now, the collapsing pressure for a short cylinder subjected to external pressure may be given by it's called the basin formula. It is, the references are Windenberg and Trilling in 1960. It's a very early paper. And the critical pressure is given by this PC is equal to 2.42 E T0 divided by DOO whole to the power 5 by 2, whole thing divided by 1 minus mu square in brackets and to the power 3/4 in bracket multiplied by H by DOO minus 0.45 T0 by DOO whole to the power half. And this bracket is closed. Okay, all the parameters we already explained. Mu represents the Poisson's ratio and PC represents the critical pressure. Okay. Now the critical pressure also for a hemispherical, elliptical, and torispherical. These are different geometrical shapes of the elliptical end. Okay, and or even for a spherical vessel, it is given by another formula. Okay, and the PC is equal to 0.5 E THO divided by RO square divided by 3 times 1 minus mu square whole to the power half. Here, RO is the only parameter which we are not discussed. RO is the outside radius of the head of the shell, and THO is the thickness of the head for the outer shell. Okay, Now, these formulas I have just listed out here, but depending on the conditions or the requirements, you will have to select the right formula from the Randall-Barron's book or ASME Section 8 Pressure Vessel Code, right? We have also written a small program in MATLAB. It is called, it is in Fortran. It is called program cryodesign.var. This will try to calculate the wall thicknesses of cylindrical shells and hemispherical shells for specific material like aluminum, copper, and stainless steel, etc. And this program, if you run, will be able to get the wall thickness of the geometry, what you are choosing. For example, if I take a cylindrical vessel, then you can calculate whether it's a short cylinder, long cylinder, and then it will calculate the appropriate formula for calculating the wall thickness. Right. Okay, we have completed more or less the design aspects in terms of the wall thickness. What about insulation? Now you need to have thermal insulation. Now the thermal insulation we are going to discuss in the next class, a detailed chapter. Okay. Now thermal insulation needed for what? You have to reduce the heat transfer as much as possible so that the storage container can hold the cryogenic fluid for long periods of time, as well as if it is a cryostat, the cryogenic conditions will exist much longer time. Now, essentially, it is meant for the heat transfer reduction. All the cryogenic systems should use suitable insulation to minimize the heat transfer from ambient. Now, there are a variety of thermal insulations are there, and you can see in the photograph some of them are shown. Okay, before we look at the contents, what is shown. So, what are the types of insulation that can be used? You can use a powder insulation, or you can use a foam insulation. You can also use evacuated powder insulation. You can have a vacuum only as insulation, or you can use super insulation, which is called multi-layer insulation along with vacuum. So all this, whatever I have listed, is in the order of improved performance. That means multi-layer insulation with vacuum will be the best possible insulation that can be used for a system. Now, again, the choice of the insulation depends on end application, ease of application, and also the cost. What sort of costs are involved in making the insulation, right? Now, let's come to fabrication techniques. The fabrication steps in a cryogenic system employs standard conventional techniques such as soldering, brazing, TIG welding, etc. Okay. Parts which are made out of copper and brass can be connected together also by special low temperature solders. So you need to use appropriate solder so that they can be properly connected. You can use silver brazing, which is one of the standard techniques for joining copper to stainless steel, copper to brass or stainless steel to stainless steel. Okay, this is one of the important methods. Now you can also use TIG welding, which is TIG. TIG means tungsten inert gas welding. These are useful for joining aluminum to aluminum, copper to copper, stainless steel to stainless steel, etc. So these are one of the methods. These are the different methods, the fabrication procedures which are used. All the metallic components are connected by the above techniques of silver brazing or TIG welding or soldering, etc. But if the systems are non-metallic components and you have to join to a metallic component, for example, typically let's consider the fiberglass reinforced plastic tubes, neck tubes for aluminum vessels, then you must use epoxy-based bonding techniques. Okay, these are the ones which are preferred for this. Okay. Now I'm going to just present to you how does one fabricate a storage diwar. What are the steps involved in fabricating a storage diwar? This is what we are going to see here. Okay. I mean, when you try to make a let's say a cryostat, etc., the procedure will be different, but most features will be the same. Okay. First of all, in a storage diwar, you have an inner vessel, you have an outer vessel. Now you must prepare a proper drawing for the inner vessel as well as the outer vessel as per the dimensions which are required. Well, let's say 100-liter diwar, that means inner vessel should have a minimum of 100 liters capacity, and additionally you will have some ullage volume, etc. Okay. It will be surrounded by an outer vessel, and there has to be an appropriate gap for the using the insulations. All those details will be involved. First of all, the design should also take care of the thermal contraction during operation. Okay, the assembly and fabrication procedures should be completely worked out. Okay, step by step. Now, after doing all this, you procure all the components, you fabricate the inner vessel, you fabricate the outer vessel, maybe not completely assembled. Maybe, for example, if I am using a cylindrical inner vessel with the dish joints, then I'll fabricate them, all of them separately. Okay. They will be cleaned, and all the components are thoroughly cleaned with suitable solvents and dried. And now they are ready for soldering, welding, or silver bracing. The inner vessel components are assembled. Maybe you, after doing all that, first you do a leak testing. Make sure that there are no leaks in the joints that are done. Okay. Then you assemble the pipes, support structure, etc. Okay. Then you also do the thermal cycling. That means you allow it to come from room temperature to low temperature, and then back to room temperature, etc. This is called thermal cycling. It is done a couple of times. Make sure that there are no leaks in the system. And the leak testing is done by mass spectrometer leak detector in some cases. Also, in some cases, it will be done by radiography. So you are, after making sure the system is totally leak tight, then we can proceed to mount it inside the outer vessel. So on the inner vessel, for example, you may have to use radiation shields, absorbers, etc. outside the inner vessel. They are to be fixed, and the outer vessel components are to be assembled in steps. In each case, leak testing should be done as and when possible. When the total system is fabricated now, then should be leak tested again by MSLD, and after everything is over, then interspace is evacuated using a separate pumping arrangement. Okay. Now, once the complete evacuation is done, the system should be subjected to cryogenic environment and for its performance tests. In most cases, long-term performance tests are needed, and they have to, because they will be evaluated for the actual performance of the system. Let's say, for example, glass helium cryostats, then it has a problem. Normally, the glass cryostats, particularly used for helium, can now diffuse through the interspace from the inner vessel, and therefore evacuation of the zone is done at regular time intervals. The people who use glass divas will already probably know about this. Now let us come to typical cryogenic system. What are the typical cryogenic systems? Okay. Now I am going to show you some typical cryogenic system. One is glass divers. Okay, you can see here a set of glass divers which are shown here in the photograph. So the typical structure is like this. Either it is a simple vertical cylinder, one into the other, and then joined at the top. And then the interspace evacuated through a particular pipe connection. Okay, now I don't know how good is the visibility of this. Are you able to see this properly? Hello?
Yes, sir, it is visible.
Yes. It's visible, right? Okay. So you have an inner vessel, and then you have an outer vessel, and there is a loose fitting cover on the top. At the bottom, there is a small connection so that you can evacuate it. The interspace can be evacuated. Okay, if it is a glass diver, normally it is silvered so that this will prevent the radiation heat transfer. Now the adjacent one here is a metallic divar of suitable size, okay, and with a thin wall neck tube, or probably made of stainless steel and so on. And this is one of the very early vessels for storage of liquid nitrogen. Okay, now there are better versions of containers are available. Okay, so now here there is a narrow neck tube right to the top. Okay, now I mean, unfortunately, I'm not seeing a photograph of this vessel here. Well, we have next bigger capacity containers, metal divars of big sizes. For example, this one is a 220-liter storage divar for nitrogen. Okay, and again, as I mentioned, the inner vessel is suspended within the outer vessel. So now you have many times the metal divars for large sizes. Okay. Now let's come to the this is as far as glass divars is concerned. Now, if you come to metal divars, then you see here a big metal divar. In this one, as I mentioned, this is 220-liter capacity metal divar. So what you are not seeing here is the actual support structure, etc., because you are only seeing the outer vessel, right? Okay, now let's come to the experimental cryostats. Now you can think of glass cryostats or metal cryostat. So first let us start with the glass cryostat. Now this glass cryostat, as you can see, has got liquid nitrogen as prevented by the liquid nitrogen pre-cooling for the radiation losses, and therefore you have an outer vessel which contains liquid nitrogen and an inner vessel containing liquid helium, right? Now helium, as I have mentioned, helium is permeable from the helium chamber into the vacuum chamber. Therefore, that interspace need to be evacuated as and when required. Okay, in this case, it's not shown, but it needs to be evacuated. Okay. Now, if you are doing let us say, an experiments of flow, so in such cases, you need to monitor the liquid levels. And for such cases, you use generally slits, okay, so that through which lights can be passed and you can monitor the liquid levels. Okay. Now, there is some important thing that this inner vessel is now immersed into an outer vessel containing liquid nitrogen. So that means inner vessel is glass cryostat, and the outer one, the inner helium vessel is a glass cryostat. Then the outer nitrogen vessel is also a glass cryostat. So, for example, a typical glass cryostat arrangement is shown here at this point. And you can also see the glass, since it can break. Okay, so safety hazards are there. So what is normally done is, for a glass system, it is surrounded entirely by acrylic shields. Okay, so that the experimenter will not be hurt in case of any blast or breakage of the experimental system. Okay, sometimes you can also paste over this cellophane tapes, so that in case of a burst, then the cellophane tapes will make sure the glass materials are not shattered and becomes fine small pieces. Okay. Now, compared to glass cryostats, metal cryostats are much better. So you see here metal experimental cryostat. Now they are suitable for use down to 1.8 K. Normally, this metal cryostats will be made out of thin wall stainless steel tubing, stainless steel systems. And it will have the liquid nitrogen radiation shields, liquid nitrogen cooled radiation shields. Then helium recovery arrangements will be there, and the vacuum space will be common. Okay, now let's look at the drawing here. So this is the innermost space where liquid helium will be filled. Then you have a nitrogen chamber, is an annular chamber. In the annular space, liquid nitrogen is filled in. So liquid nitrogen entered from A, and then the night evaporating vapor goes at the A out. Okay. So this is the way it is normally done. Now, the vacuum space is common for both the inner vessel as well as the outer vessel, the liquid nitrogen shielding. So the interspace is evacuated. For example, the evacuation port is shown here. Okay. Now, in the inner space, inner vessel, liquid helium can be filled in. And when you fill in liquid helium, it is subjected to the radiation from the top, although the sides are all protected because the sides radiation comes at only 77 K. Okay. So to prevent the thermal radiation of the outside to come inside, so you use number of baffles. So you can see the horizontal lines, the number of baffles. They make sure that they are the radiation shields. They make sure that not much heat transfer comes from the outside, from the topmost point of the inner vessel to the inside, to the material chamber. Okay. Now you also introduce safeties on the inner vessel in case of any blocks, and so the safety valves will open and make sure that the pressure is brought down. Okay, what about the cool down of the metal cryostats? Now, at high temperature, normally one has to apply pressure on liquid helium when doing the experiments, and therefore you require high wall thickness for the inner vessel. On the other hand, you have to minimize the heat transfer, then you require low wall thickness. So these are conflicting requirements, and normally 5 psi overpressure is chosen in the design, and the bursting and buckling pressures are to be calculated for the wall thicknesses of the inner and outer vessels, and whichever is higher, you select that higher value so that you will make sure that the system does not have any bursting or collapsing conditions. Okay. Now the cool down procedure is to minimize the consumption of the cryogen is like this. If you start with room temperature, then you first cool to 77 K. Suppose it's a helium cryostat system. From room temperature, you cool down first to 77 K with liquid nitrogen. Then you remove all the liquid nitrogen out, and then make sure you come to 77 K to 4.2 K. So it is done 2 steps. Okay. Now the amount of cryogen required for cooling a given thermal mass is shown in the table. For example, here, the amount of cryogen in liters required to cool 1 kg of a metal in different temperature ranges are given here. Now, when we do this, you can have the following conditions. One is you can use only the latent heat vaporization, okay, or you can also use the complete enthalpy of the total enthalpy of the system, right from the temperature T to 300 K. Either one of them is possible. So, for example, we'll talk about, let's say, if I use nitrogen, I'll go from 300 Kelvin to 77 Kelvin. So, for example, here, the 300 Kelvin to 77 Kelvin, we are using liquid nitrogen. Now, what the table shows here is different materials like aluminum, copper, and stainless steel, for which A corresponds to the that I am using only the latent heat vaporization, and B corresponds to I am also using the using the total enthalpy of the system. So when I use the total enthalpy of the system, obviously the amount of cryogen required will be smaller. So let's try to talk to this one. Aluminum, let's say A is 1, that is only latent heat, whereas latent heat plus additionally the cooling capacity, then it becomes only 0.63. Similarly, for copper, it is 0.46 and 0.28. Okay, for stainless steel, it is 0.53 and 0.33. Now, you can also do one thing. After cooling down to 77 K, then you can introduce helium in the system, And that helium will now allow the system will now cool down from 77 K to 4.2 K. Now, if such a thing happens, that is, it's called liquid nitrogen pre-cooling. If such a thing happens, then for aluminum, from cooling from 77 K to 4.2 K, you require about 3.2. Okay, if I am not using the lead heat vaporization. Whereas if I am using the lead heat vaporization, then I require very small quantity, which is only 0.2. And similarly, in the case of copper, it is 2.2 and the case B is 0.16. In the next case, it is 1.46 stainless steel, the case 1.4640, and whereas on the other hand, this is only lead heat vaporization. If you don't if you use the total enthalpy, then it's just only 0.1. Okay. Now, it's also possible that I do not want to contaminate the system with nitrogen. So somebody can decide that I would like to start with 300 K and then reach 4.2 K directly with the cryogenic fluid, namely helium. In such a case, the values are fairly fairly large. For example, in the case of aluminum, it is about 66. If we use the cooling capacity in terms of enthalpy, then it's only 1. And in the case of copper, it is 32, only lead heat vaporization. But I'm sorry, there is this data is wrong here, 32. It's about 1.2. Okay. Then the last one is, for example, stainless steel, it's about 3.34, and it is a value of case B will be only 0.8. That means we are using the total enthalpy of the system. Okay. Now, before we proceed to the continuous flow cryostats, I will take a break now. Is it okay? Hello?
Yes, sir.
I will just stop here for time being. We will come back in another 7 minutes. Okay. What's
Okay.
now?
10:55.
Okay, fine. So we'll start somewhere around 11:02 or 11:03, around that place. Okay.
Okay.
Take a small break now. Hello, Rahul,
Yes, sir.
are you people there?
Yes. Yes, sir.
Our discussions. In the earlier section, we saw about the design of storage vessels as well as cryostats, standard cryostats of glass as well as metal cryostats. See, there are also other type of cryostats which are there, which are called continuous flow cryostats. Let me make this full screen. I think I have not done that. Okay. Now, this continuous flow cryostat is designed such that it uses very less quantity of cryogenic fluid. Okay, the methodology is very simple. All that is done is you take the cryogenic fluid from the bottom of the cryogenic tank, storage tank, through a small transfer line, and it is allowed to circulate around the chamber which houses the sample for experiments. And it is also used, the outgoing vapor is also used as a radiation shield. Okay, on the radiation shield, the same pipes are wound completely, and before it exits to a pump, to the mouth of a pump. Okay, so what is the advantage of such a system? The advantage of this system is you are not directly dipping your sample inside the cryogenic fluid. Instead, you are using the complete enthalpy of the cryogenic fluid for cooling. So this is called continuous flow cryostat system. So as you can see in the design, there is a bottom port through which liquid helium is sucked inside. And it is now, I mean, these are all sectional, this is a sectional view. So there are large number of coils, okay, just wound over. So the bottom first it is winding is done, and then next it is wound on the walls. And then after completing up to the neck of the wall of the innermost chamber, then it is switched over to the radiation shield. And then from the radiation shield bottom, it goes out to the pump. Okay. So this is the way it is normally done. The whole thing is covered with super insulation and then a vacuum jacket. Complete vacuum jacket is there. Provide that vacuum is, the vacuum is created by a separate pumping arrangement. So now the vacuum pump sucks the cryogen from the storage reservoir through the transfer line. The cold vapor passes through the copper lines wound over the sample chamber and cools it. And then radiation shield surrounds the sample chamber. Again, this radiation shield also is cooled by the outgoing vapor from the sample chamber part. Okay. Now the flow of cryogen is always adjusted by a suitable needle wall at the pump inlet, and that needle wall arrangement is controlled by what is called the electrodynamic valve. It's called the electrodynamic valve. Okay. So this is an arrangement which is normally done. Now you can see the total arrangement of the continuous flow cryostat. You can see here there is a storage reservoir, and from the storage reservoir a transfer line is directly connected, and then this is the sample chamber, and the cooling takes place on the sample chamber. The same coils cools also the radiation shield, and from the radiation shield it goes through the electrodynamic valve to the pump, and then it goes to the recovery. And the electrodynamic valve controls what should be the sample temperature. So a temperature control is automatically incorporated. So it allows or adjusts the quantity of the cryogenic fluid that is taken out, that is pumped into this whole chamber. Now this continuous flow cryostat was invented by Professor Gutsav Clipping. So it is called Clipping continuous flow cryostat system. That is the way it is named after him. Okay. Now there are also other commercial experimental cryostats. These experimental cryostats are available from different companies. I have chosen the drawings from Janice Research Company, United States of America. So for example, the one on the extreme left, for example, this one is actually a simple liquid helium experimental cryostats. Okay, so the liquid helium, so it is shielded with the liquid nitrogen. So nitrogen supply and this vapor, nitrogen supply and supply into this chamber, and also its own vent, etc., is separately monitored. The liquid helium is passed to the innermost chamber, okay, innermost reservoir, and there is a common vacuum space again, as it is mentioned. So you can evacuate the common vacuum space by a suitable valve and by connecting to a pump. Okay. Normally, you can see the upper parts are all welded properly. Okay, proper welding is done either by TIG welding or silver bracing, etc. But the bottom parts are, okay, these are indium seals. Whenever the temperature is very low, and the outermost chamber is done with the O-ring seal because it's going to be at room temperature. Okay, so the first drawing what you have seen here is a simple liquid helium cryostat. Okay. Next, we have another system. The second system is like this. This one is a tailed cryostat, a cryostat which has got a long tail. Okay. And this cryostat is preferably useful for optical purposes. You have an optical window. Okay. You can shine experimentally. You can now pass the radiations, etc., through this, and this can be done for that. Sometimes, along with the radiation, you can also subject it to a magnetic field, an external magnetic field through this. So here, the procedure is like this. You fill up liquid helium into the liquid helium chamber, but through a small needle valve, the liquid helium enters the sample chamber and completely goes into the sample space. So the sample will be cooled by the cold vapor of helium, which is starting from the liquid helium chamber. Now, by using a temperature controller and heating arrangements and by the adjustment of a needle valve, you can allow the quantity of helium, control the quantity of helium that is entering the sample space. So this is the arrangement for this purpose. This is again having a nitrogen, liquid nitrogen shielding, okay, which has its own independent, and sometimes it can have a common vacuum space, or it can also have independent vacuum space. Okay, so this is the second arrangement, typical cryostats. Now we have a third arrangement of the cryostat in which you have a superconducting magnet already embedded, already kept inside liquid helium. Okay, and it can be charged at will. That means you can pass current to make sure it becomes superconducting. And once it is in the liquid helium zone, when it reaches the temperature of liquid helium. So this again is surrounded by a liquid nitrogen jacket as a radiation shield. Okay, and both the liquid nitrogen and liquid helium chambers have common vacuum space, and they are evacuated by an appropriate, evacuated through a valve and connected to an external pump. So these are commercial experimental cryostats which are available as per the requirement of the user. One can buy these cryostats and then use for the application. Okay. Now let me discuss about the cryostats for cryocoolers. Now the cryocoolers normally replace the cryogenic fluids. Okay, as you have seen, the cryocoolers produce the refrigeration power as required at required for your experiments at the desired low temperature. Okay. In fact, by using a cryocooler, you can also have different temperature conditions for your sample, and the higher the temperature, more will be the refrigerant power available. Now, sometimes it is possibility of continuous operation. For example, if I want to have a superconducting magnet, operating the superconducting magnets continuously, then I need to use a cryocooler for that purpose. Now, there is a possibility of continuous operation in such cases. And now also it avoids the use of filling of liquid helium, etc. Of course, the necessary electrical power for running the helium compressors, etc., need to be provided into the cryocooler. Now, what about the cold head of the cryocooler? That forms the actual experimental station. Say there can be a single stage system or a two-stage system. So the cold head of the cryocooler, okay, which forms the experimental zone, now that needs to be surrounded by a suitable vacuum jacket so that the system is completely isolated from the surrounding or minimize the heat transfer coming from the ambient to the cold head of the cryocooler. Say, for example, so that means this is what is called a vacuum jacket for the cryocooler. Okay, you also have normally if you have two-stage cryocooler, if it's a single-stage cryocooler, then you provide a suitable radiation shield. If it is a two-stage cryocooler, the first stage cooling power of the cryocooler itself is chosen as the radiation shield, for the second stage. Okay, a typical cryocooler using lead as the regenerator will go up to 10 Kelvin, 8 to 10 Kelvin for the second stage, and almost about 35 to 40 Kelvin in the first stage. Okay. And if you are using a special regenerator material like erbium-3 nickel, holmium copper, etc., as we have discussed earlier in the case of cryocoolers, so these things can go to temperatures like almost 2.8 Kelvin in the second stage, and in the first stage about 30 to 35 Kelvin. Okay. Now, you can see here, for example, a cryocooler mounted. Okay, this is the second stage, and the first stage is connected, and the first stage will now serve as a radiation shield in this case, and the cryocooler room temperature zones are connected to the appropriate piping and cables, etc. Okay, and you have a vacuum jacket which is surrounding this. This needs to be the cryocooler needs to be super insulated, and then also the radiation shield, and subsequently the vacuum jacket is put on the top of that. The interspace is evacuated. Many times you need to provide appropriate electrical feed throughs, etc., which will carry the signals of whatever you are measuring. Right. Now, I would like to show you a pulse tube cryocooler which has been developed at Center for Cryo Technology, IASC. It's a two-stage pulse tube cryocooler. And as you can see in the pulse tube cryocooler, this forms the first stage, and this forms the second stage. The red thing, what you see here is only the adhesive tapes of colored red, nothing very specific about it. And this one is the actual experimental setup. This cryocooler is to be super insulated and then inserted into the vacuum jacket, which is this is shown the vacuum jacket. Okay, and then connected to a helium compressor through a rotary valve, and the rotary valve, by rotation of the rotary valve, by the rule-on of the rotary valve, then the high and low pressure pulses are applied to the pulse tube, and you produce the cooling. In our typical experiments, we have been able to reach a no-load temperature of about 2.5 Kelvin in our pulse tube cryocooler system. Okay. Now let me come to bigger cryogenic systems. Now this, for example, is what is called DESY, Deutsche Electron Synchrotron module, cryo module. And you can see here, this is for the accelerator purposes. And you can see the cryostats which are mounted. They are all large number of cryostats assembled together, one over the other. And this is one section of this cryo module. So you can see when the systems are this big, then appropriately you need to provide the vacuum pump for the evacuation of the vacuum jacket, etc. Right? Okay. Coming to the international thermonuclear reactor, this is one of the very big cryostat systems. This is now under construction, or maybe now the construction is more or less completed in a place called Catarache in France. And this is a joint collaborative program between many countries. India is also one of the partners, and maybe 6 or 7 countries. India is also one of the partners for the program, and they provide basically the cryolines and the cryogenic systems. This cryogenic system India is providing for this. Okay, there are a lot of people who work in the Institute of Plasma Research in this particular program, and they take care of many things. Okay, basically what it is having a superconducting magnets. The superconducting magnets are in the form of a D-shaped for what is called the toroidal coils. These are toroidal coils. Okay, and there are also poloidal coils which are mounted on the top and the mid zone and the bottom zone. These are the poloidal coils. For example, I think this represents a poloidal coil. Okay, and you have a zone wherein the magnetic field is now is confined into the center of this arrangement. So the charged particles or plasma, because it is a charged particle, it is nothing but a current, and the current will be the charged particle will be completely confined within they move in the form of a helix continuously in this loop, continuously within this. Okay, so the charged particles are totally confined in this arrangement. So this is what is called the International Thermonuclear Reactor, and this particular program is on, and most likely this is an experimental reactor. So you will try to produce power output from the nuclear fusion reaction. The fusion with the tritium to form helium and neutrons and plus energy. So this is the reaction that will be chosen. Okay. I have more or less discussed about the cryogenic systems. Next, I am going to talk to you about cryogenic transfer lines. Okay, what are the cryogenic transfer lines? As you are fully aware, a transfer line enables the transfer of cryogenic fluid from one location to another. So it is used for transferring the cryogenic fluids from one location to another. So the transfer lines can be of different type. It can be a rigid type transfer line, or it can be a flexible transfer line. If it is a rigid type transfer line, it uses rigid pipes. Okay, for example, one tube over the other tube. So it's a simple, rigid piping which is used for this purpose. For example, you can see here the top is representing a rigid transfer line. So this will take the cryogenic fluid and then allow to flow to the other side. This is typically for I think for transfer of cryogenic fluids like liquid hydrogen or liquid helium from a storage DVAR into a continuous flow type cryostat system. For that, this type of transfer lines can be used. Now coming to the flexible transfer line, the flexible transfer lines are prepared using bellows. Okay, the inside is a bellow as well as the outer jacket. Inside part is a bellow and outer jacket is also a bellow, and because of which there are a lot of flexibility is available in the design and mounting arrangements, etc., for the flexible transfer line. Okay, the initial cool down from ambient to cryogenic temperature always happens whenever you first start using it. Okay, from room temperature you start using it. So therefore, you need to have a cool down of the transfer line from the room temperature to low temperature. Okay. Now, because of this, the incoming cryogenic fluid is vaporized, and also there is going to be some amount of heat inleak into the system. So two-phase flow is one of the common phenomenon. What do you mean by two-phase flow? The phase of both the vapor and the liquid flowing through this. That's a very common feature in the system. Now coming to so you should make sure the heat transfer is completely minimized and the liquid flow is maximum at the outlet. Okay, so that the liquid flow is maximum at the outlet, because then only the user will have the benefit of having maximum liquid for his experiments. So also one should note that when you have a long line like this, then you have a thermal contraction of the inner line, because the inner line is going to be cooled. Okay, as far as the flexible transfer line is concerned, automatically it is taken care, because the inner line will try to contract, but since it's a bellow, automatically the contraction is taken care by the bellow. Whereas in the case of rigid lines, you need to introduce additional bellows. This bellow can be introduced either at the inner one or at the outer one. That is, inner jacket, you can introduce a bellow, or you can also use on the outer jacket. Using on the outer jacket is outer line has the advantage that in case of a repair, you can automatically attend to it. Whereas inside inner line means you have to dismantle and then to look into the leakages and so on. Okay. Now coming to the transfer lines, you can think of several types of transfer lines. One transfer line is uninsulated line. That means just bare lines. Okay. The bare lines, these are useful for simple transfer, for short time transfer. Okay. Cryogenic fluid from one side to the other. For example, if I have a storage vessel and I want to transfer some small quantity of cryogen into another vessel, then all I do is I use a bare vessel, bare line. So I put a bare pipe, then which is tightly sealed at the top. Then you introduce high pressure into the inner vessel, then the liquid is carried and then goes to the receiver. Okay, but then it is exposed to the surroundings, and therefore moisture, carbon dioxide deposit on the line. But anyway, the transfer is going to be short time, so there may not be much of a loss in this type of using this type of transfer lines. You can also use insulated transfer lines. So you can think of insulation like foam, fibrous insulated lines. Now, I have not done the thermal insulation. I will do the thermal insulation shortly. Next lecture will be of thermal insulation. So we can use foam or fibrous insulated lines. You can also think of fiberglass, polystyrene, polyurethane, foam, etc. All these things can be useful as insulation. Okay. You can use vacuum insulated lines. You can, for example, use only vacuum as the insulation. Okay, that means the inner line, and then it will be surrounded by outer line. The interspace will be evacuated. That is called just vacuum transfer line. Then you can have vacuum insulation along with multi-layer insulation. So in other words, it's called MLI insulated transfer line, because multi-layer insulation will be effective only if you use vacuum along with it. So use that type of arrangement. What is multi-layer insulation? Multi-layer insulation is nothing but multiple layers of super insulation material. It takes care of the radiation which is coming from the ambient to the cryogenic fluid. Okay. The shields are made out of let's say aluminized mylar separated by a spacer, or aluminum foil separated by spacer. So these materials have low emissivity. Because of low emissivity, the incoming radiation is minimized as much as possible by use of these. An optimum number of insulation layers are chosen so that the heat transfer by radiation is minimized. At the same time, conduction heat transfer does not go to very high values. Okay. Now, in the case of transfer lines, you can have two types. Either you can have a rigid transfer line, or you can also have a flexible transfer line. Okay. Now, I am going to show you a rigid transfer line, which is a very simple vacuum insulated, or it can be super insulated type transfer line. All that is done is you have an inner line surrounded by an outer line. Initially, they will all be, okay, initially they will be at, it's a total horizontal line. Now, then you can do what is called the cryo bending of the inner line. If you are not going to do a cryo bending, then appropriate connective connection portions have to be chosen for making the zone. Okay, if you do a cryo bending of two pipes simultaneously, okay, then it is possible to have bending like this arrangement. Okay. Next, the shrinkage of the inner tube with respect to the outer line has to be taken care, because these two ends are welded. So obviously there is going to be a shrinkage. It should be taken care such that at the time when it shrinks, the piping should be all centered, okay, one into the other. Okay, particularly the inner and outer lines should not touch. And if they touch, then what happens? There is a shorting, and because of that, heat transfer will be very high from the outer pipe to the inner pipe. So large loss of cryogenic fluid will be possible. Okay. Many times you also require a spacer. Typical spacers are required in between so that the inner line does not touch the outer line. And there are several spacer designs are used. For example, this is what is called the triangular spacer. This spacer is not only for the purpose of making sure that the inner vessel does not touch the outer vessel, also to make sure the heat transfer, okay, of this support arrangement is as small as possible. Okay, for example, the supporting area at the room temperature is very small, and whereas it is touching over the inner line, completely, totally touching over the inner line. Okay, next, so you can have either a triangular type or a, let's say, square type, or including you can also have a roller type of arrangement. A roller type of arrangement also can be used in these cases of this type. Okay, so this makes sure that in case of a thermal contraction, there is a possibility of the inner line to move with respect to the outer line. Okay. Okay, vacuum insulated rigid and flexible transfer lines are shown in this photograph. Okay, you can see here the inner line is a rigid line and the outer line is also a rigid line. The outer line uses a small bellow. Make sure that thermal contraction is taken care. And there are spacers of different geometrical shapes, okay, which are mounted in between the inner and outer line. Okay. So you need to evacuate the the space in between. For that, you require an appropriate vacuum port, which will be connected by a special valve arrangement to the vacuum pumping system. The inner space, the spaces will be appropriately evacuated. This, for example, this photograph is, for example, is an arrangement for in the case of a flexible transfer line. In the case of a flexible transfer line, the inner line is flexible type bellow, and similarly the outer line is also a flexible bellow. The interspace is evacuated by bringing them to rigid sections and then connecting, for example, the appropriate ports for evacuation purposes. Okay. So the ends of the flexible lines, it forms a rigid section, and the cryogenic fluid will pass through this particular central pipe. Okay, I am showing you the photograph of a 3-meter long flexible transfer line, which has been fabricated at IISc, and a student has been able to complete his PhD work on this one. So this, for example, is the inner bellow, okay, bellow line, and you see certain ring-like things at the body of this. They are nothing but spacers. Okay, he has used bakelite material as a spacer material. It's just a bakelite ring which touches the inner vessel as well as the outer vessel. Okay, so this is the way in which it's done. Now, the inner bellow is put inside the outer bellow, put inside the outer bellow, and the end couplings are all fitted, and this assembled the 3-meter long demountable flexible transfer line is what is shown here in this diagram. Okay. You can also do the experimental arrangements. Think of an experimental arrangement for evaluating its performance. What is the performance evaluation? What they do? What they do is they will like to find out how much is the quantity of cryogenic fluid that is transferred through this transfer line. Okay, and how much is vaporized, how much liquid one is able to collect. Okay, and what sort of pressure drops that happens over the length. So the transfer line this is the transfer line which is mounted on an appropriate stand, and the inlet of the transfer line is connected to a standard storage diwar, nitrogen diwar. Okay, and there are pressure transducers which are mounted along the length to measure the pressure of the cryogenic fluid that is passing through this. And the end again, you have the discharge from the transfer line is collected in another storage diwar. Okay, so this is an experimental setup which is available for testing different transfer lines. We have also developed a 5-meter long transfer line. So this is somewhat longer than this. So these things have been done. A 5-meter long transfer line has been done. Now, these are done because of the based as per the requirements of a BRNS project for transferring liquid helium. So, for example, you can see here the appropriate end coupling, what is required as per the requirement of the user. Okay, and this is an experimental line, so people have used feed-throughs, but in a practical line where there are no experimental no experiments are going to be done with that line, then in that case this can be avoided. Okay. Now let me discuss something about the transitions that go in between the transfer lines. These are known as bayonet couplings. Okay, there are a lot of special designs to ensure that the outer jacket is maintained at room temperature, whereas the inner jacket carries the cryogenic fluids. Okay, the thermal contraction of the inner tube is also to be taken care in the design. The liquid flooding, okay, to the warm end should be as minimal as possible. Okay, now you can see here the structure is such that the room temperature joints are over here, whereas the low temperature joints are little far away from here. What normally happens is if there is a cryogenic fluid that is flowing through the inner pipe, then small quantity of fluid will enter into the gap in between, and then it will pressurize the space. Okay. By the time it reaches the room temperature zone, it is almost warm. Because it is warm, but at the warm zone, it is all sealed. It cannot escape anywhere. So therefore, it goes back into the same path and then stays there as it is. So by this type of arrangement, this was called known as bayonet coupling. By this type of arrangement, the room temperature zone is always maintained at room temperature because this fluid shuttles between these 2 points. It maintains the room temperature at the room temperature zone itself. This is what it does. Okay. Now the liquid flooding to the end warm end is now minimal because of this reason. And the bayonet coupling can also be field welded by as shown in this figure. So what they are normally doing is you have a piping and you have another piping at the opposite end, and you have an intermediate zone where the outer zone is fixed with the appropriate, let's say, a plate. And then that plates are joined together, okay, using the appropriate welding arrangements. So this will be again a field welded type of joints between the two transfer lines. Okay. See, for example, this particular figure shows you that there is an internal bellow. The bellow is in the inside internal part. The bellow takes care of the thermal contraction between when there is an inner vessel shrinks with respect to the outer vessel. Okay. So this is the simple arrangement for doing this. Okay, what are our experiences in cryogenic transfer lines? I would like to just spend a couple of minutes on this one. We have been able to make LN2 liquid nitrogen transfer lines at our center. So this transfer line carries the cryogenic fluid from the main storage tank, which is kept outside the department, to the cryogenic plants for liquid helium plant operation. And many times, the tank which is kept outside is also able to take care of, is also filled with the cryogenic fluid that is produced by the plants. Two plants, the PLN 430 machines, which are kept in these zones. So, for example, I'm not able to, yeah, in these zones. These are the connections for this one and this one. Okay. So they are connected from the liquid nitrogen supply. Okay, the liquid nitrogen supply, after which once the valve is open, it goes to either the plant or it goes to the receiver. It goes to the receiving zone. Okay, so these are the type of arrangements. Now, what we have done is in this case, we have used almost about 1 inch type of piping for the inside, and approximately about a 2-inch pipe for the outside. And this is entirely done with a flexible bellow arrangement. Okay. So this system is available. So I think the details of the pipings, etc., are given here. I may not have time to go through this. The inside may be, sorry, I may not be 1 inch, it may be about half an inch, and the outs may be about 1 inch or 1.5 inches. So you can see the entire bellow that is fabricated here. So the cryogenic plant, from there it is connecting to the common thing on the top, and from there it is supplied to the storage tank. Okay, these are different section views, and it is also used for supplying liquid nitrogen to the helium plant for pre-cooling. Okay, so this is the piping which is coming on the wall. It is connected to the liquid helium plant. Okay. We are also able to make a remote delivery tube, which is a special tube for helium, for nitrogen transfer from the liquid nitrogen plant. The design is such that you have minimal heat transfer from the room temperature zone to the low temperature zone. Okay, I'm not able to go into the details at this point, but as you can see here, this is the outer tubing, and it is connected to the inner vessel tube, multiple pass, right? And the liquid nitrogen, whatever is produced, comes through this and falls directly into the storage tank. We are able to make also a remote delivery tube for a liquid helium plant. Okay. And with or without JT, the one what you see on the left side is without JT. This is even today it is functional, and it is it has been done with using thin wall stainless steel tubes for both for the inner as well as the outer tubing. Okay. Now it is a super insulated type of system, and which is performing quite well at our place. We also have made a remote delivery tube with integral Joule-Thomson wall at the Diwar side, receiver Diwar side. And this wall, when you operate, then the JT, the gas gets expanded, and the JT produces cryogenic fluid, and the fluid is directly connected into the storage vessel. So we have got a patent of the remote delivery tube with integral Joule-Thomson wall, and it is also a publication in Cryogenics journal. Okay, so far I have discussed about the cryogenic transfer lines. Okay, I'll spend another maybe 10 minutes or so on cryogenic valves and safety devices. Okay, first of all, why we'll talk about cryogenic valves. The cryogenic valves are needed for either shutting down the flow of fluid or to allow the flow of fluid. So it is needed on the lines. For example, if I have a cryogenic tank, at the end of the cryogenic tank, I should have a shut-off valve so that cryogen is not wasted. It is able to hold the cryogen within the cryogenic tank. Okay. What are the normal designs? The normal designs are standard valves, whatever that are used. You need to modify them with such that they have long stem, because we need to ensure low heat leak inside and also low pressure drop. So what is normally done is one modifies the standard designs of popular globe, gate valve, plug type, or butterfly valves, or ball valves, etc. They are used, which are used in chemical industries, and they are modified accordingly. For example, you can see here long stem, valve. This is probably simply a gate valve, okay, or a plug valve, a globe valve. And this you can see here a short stem valve. When you have a considerable transfer of cryogenic fluid, it actually collects on its outside large quantity of moisture and carbon dioxide. Now, in a cryogenic valve, the stem is always extended, as you can see here. This is an extended stem valve. Okay. Now, let's come to the safety aspects. In a cryogenic device, you require a cryogenic system, you require safety devices. This is because any cryogenic fluid will, when it vaporizes, it produces almost 700 times that of the vapor, 700 to 800 times the vapor quantity. For example, 1 cc of liquid nitrogen will evaporate to almost about 750 to 800 cc's of vapor, liquid nitrogen. If the system is permanently closed, then you are building up a pressure of almost about 750 bar. So this will be safety. It is not a suitable safety arrangement. So you need to make sure that this high pressure is vented off. This is done by in two ways. One way of using it, what is called a safety valve. This is a spring-loaded valve. So when the pressure exceeds a set value, automatically the spring is opened and the gas goes out through the opened area. Okay, this is the first level of safety. When the first level of safety fails, then you need to incorporate a second level of safety, and that is done by a bursting disc. Say a small disc with a thin metal sheet is allowed to be punctured. Okay, normally it will not be punctured. Normally it will be closed, so that it takes care of the vacuum. But when case of leakage of cryogenic fluid into that, it expands and it makes sure that it is punctured. You can see here the puncturing is shown here. Okay. And in case it is damaged like that, then automatically one has to remove and replace it by a new one. Okay. I think I will conclude now. I have discussed with you the cryogenic system designs. And of course, it depends on the end application, what exactly you are going to use it for. For example, it can be a cryocooler vacuum jacket, or it can be a cryogenic storage vessel, or it can be a cryogenic experimental cryostat, etc. So depending on the end application, you should make the design. Secondly, the design should be based on several criteria as mentioned. The formulas, design formulas which have been available, one has to completely strictly follow these procedures in the development. And a very good book is by Randall Barron, gives you most of the details about the having a proper cryogenic system built. Okay. There are a number of other references as well. And there are books by Timmerhouse and so on, which are very much suitable for the your development of cryogenic systems. Okay, I think this is all I would like to mention. There are a number of reference books I am showing you here. Cryogenic Systems by Randall Barron, and then Introduction to Cryogenic Engineering. These are written by the scientists from CERN. And then Cryogenic Engineering by Russell B. Scott, R.B. Scott. Cryogenic Engineering by Thomas M. Flynn. Advances in Cryogenic Engineering by K.D. Timmerhouse. And there is also a textbook of cryogenics by Kostyonk. Okay, there are a whole lot of other references, which if you are interested, you can go to them and then read it. So I thank you very much for your patient listening.